Hey everyone. So when you get into higher level math and physics, you start running into these equations that just look, well, chaotic. But what if I told you there's a way to sort most of them into just three simple groups? And the best part? The key is a little tool you probably learned back in high school algebra. Let's dive in and see how we can bring some order to all that chaos.
You remember this, right? Good old conic sections. You get some messy equation with x's and y's, you do one quick little calculation, and boom, you know if it's an ellipse, a parabola, or a hyperbola. It was a super neat trick. Just kind of tuck that idea away for a minute.
All right, so we're going to take that exact same idea and apply it to something that, let's be honest, looks way more intimidating. We're talking about second-order linear partial differential equations, or PDEs for short. And this stuff is a huge deal in multivariable calculus, because these equations describe pretty much everything around us.
Okay, here's the general form. I know, it looks like a total mess of symbols, right? You've got multiple variables, second derivatives, it's a lot. But here's the thing. Just for now, ignore everything after the first three terms. I just want you to focus on those coefficients A, B, and C. Seriously, that's where all the magic is.
The secret to cracking this entire complicated beast of an equation, it's a simple little tool that I promise you've seen before. It all comes down to boiling everything down to just one single number.
And there it is, the discriminant, b squared minus 4ac. Yep, the exact same one from conic sections and the quadratic formula. This little guy is our secret weapon. It's the diagnostic tool that tells us the fundamental nature of the whole equation. You see, the sign of that one number, whether it's positive, negative, or zero, sorts all these complex PDEs into three distinct groups. I like to think of them as PDE personalities, because each one describes a totally different kind of physical behavior.
This table lays it all out. It's pretty straightforward. If b squared minus 4ac is positive, the equation is hyperbolic, and it describes things that act like waves. If it's zero, it's parabolic, and it's all about diffusion, like how heat spreads out. And if it's negative, the equation is elliptic, which describes systems that are in a state of balance or equilibrium.
Okay, that's enough theory. Let's make this real. We're going to walk through a couple of the most famous PDEs you'll ever see and see how easy it is to classify them.
So first up, we have the classic wave equation. This is the math that could describe, say, the vibration of a guitar string. Our mission is to figure out its personality.
The process is always these three simple steps. First, we've got to identify our coefficients. Now be really careful here. A is the number in front of the u sub x term, which in this case is -9. That minus sign is so easy to miss, so watch out for it. There's no mixed derivative term, so b is just 0. And c in front of u sub tt is 1. Now we just plug those numbers into our formula.
So we calculate b squared minus 4ac. That's 0 squared minus 4 times -9 times 1, which gives us a nice, clean 36.
And since 36 is obviously greater than 0, our rule tells us the wave equation is hyperbolic. I mean, that just makes perfect sense, right? It's called the wave equation, so of course it has a wave-like hyperbolic personality.
All right, next example, the Laplace equation. This one describes things like the electric field in a space, or how heat is distributed once it's all settled down. Now, you might notice the variables are x and y here instead of x and t, but don't let that throw you. The process is exactly the same.
Let's do it again. Step 1. Find the coefficients. A for the u sub xx term is 1. B for the mixed term, well, there isn't one, so b is 0 again. And c for the u sub yy term is 1. Okay, step 2. Time to calculate.
We plug them in 0 squared minus 4 times 1 times 1, which works out to -4.
And because our result is less than 0, the Laplace equation is elliptic. And again, this totally fits. It describes systems in equilibrium, and that is the classic signature of an elliptic equation.
So far, so good. The equations we've seen have had one fixed personality. But what happens when an equation can have more than one? Let's check out a really fascinating example that takes us from pure math straight to the physics of breaking the sound barrier.
So meet the trichomy equation. Now look really closely at the a coefficient, the part in front of u sub xx. It's not a number anymore, it's the variable y. And that one little change has enormous consequences. See, when we calculate b squared minus 4ac this time, with a being y, b being 0, and c being 1, we don't get a fixed number. We get an expression, -4y.
This means the personality of the equation actually changes depending on where you are.
And this is what we mean by a mixed-type equation. In any region where y is positive, our discriminant, negative 4y, will be negative, so the equation acts elliptically. But if you move to a region where y is negative, the discriminant suddenly becomes positive, and the equation's whole behavior flips and becomes hyperbolic.
So why on earth is this so important? Well, it turns out this mathematical flip from elliptic to hyperbolic behavior is a pretty amazing model for what happens to the air flowing over an airplane's wing as it breaks the sound barrier. The actual physics of the airflow changes type, right along with the math. How cool is that?
So, there you have it. A really simple idea from basic algebra, the discriminant, gives us this incredibly powerful way to classify and understand these super complex physical phenomena. It takes the apparent chaos of these equations and gives us a clear, organizing principle. And it kind of makes you wonder, right? What other complex systems are out there, just waiting for us to find the right key to unlock their secrets?